Okay, I guess we're waiting for a couple of minutes to let people join, and then we'll start.
Sounds good.
We are gonna be leading the discussion session for the last lecture of the school. The last lecture is gonna be statistical mechanics of machine learning, and the lecturer is gonna be David Schwab, and I am Wave. And this discussion session is also led by Tankut and Mingwei. Okay, so the first part of this is about what is machine learning, and I would like to get everybody on the same page so we understand what we're talking about. So let's get started. So there are like two fundamentally different data analysis paradigms, estimation and prediction. Let's imagine you have a pendulum like this, and then you go and measure the period of this pendulum as a function of the length between like the mass and the ceiling, and you get some experimental data. So the estimation paradigm is about estimating a parameter in a model. So in this case, you would know physics, and the question would be, what's the gravitational acceleration G in the formula, in this formula here. So this comes from physics, and we know that it should obey this formula. And now we have data, we want to determine what the parameter of the model should be. But in the prediction paradigm, we wouldn't know any physics. We don't know how these data are generated, but we want to ask what would be the period of new pendulum in new experiment. So we want to predict, and we don't have any written model beforehand. Okay, so machine learning focuses on prediction as opposed to estimation. So what we would call pre-data science is how we usually do physics in the past would be the way that we try to capture the model parameters using the data. So in this case, if you want to have to do like a good estimation, you need a good model, which require insight into how these data are generated. In this case, you would need to know physics in order to come up with the formula in the previous page. And the parameter that we try to estimate usually have meanings. In this case, it will be the gravitational acceleration. And also in the pre-data science paradigm, the number of data points is usually much greater than the number of parameters in the models, which is approximately of order 1. Okay, and in machine learning, the goal is quite different. We want to get some models that can accurately make prediction on new data. So in this case, model parameters are usually do not have meanings on their own. So the model can be complicated, can be anything. We are agnostic about how the model should be. But for neural network, usually the number of data point is roughly the same order as the parameter in the models, and sometimes model can have millions of parameters. So this brings in like a lot of different scale that you do not have in the pre-data science and data analysis. So we talk about prediction, and now how do we measure predictive performance? So the way that is done in the modern data science and machine learning is that first thing we divide the data into training data set and test data set. For example, in this case, you have all these data set. You just randomly assign these data set into training data and test data. Usually the test data would have about 10 to 15% of the original data set. And most of the data we would use for training. And after you have divided the data into the training data set and test data set, what we do is we now fit a model by minimizing error on training data set only. So we treat this data as if we don't have any test data set at all. Sometimes test data set is also called whole out data set. So you don't see this at all. What you see is only the rate data point, and then you try to fit the error by, to try to fit the model by minimizing the errors. Let's suppose like this yellow line is our model, is the best fit of our model. Now, the third step is to compute model error on test data set. So now we take the model that we fit on the training data set, and then we're gonna use it on the test data set, and then we compute the errors. And this error is a measure of predictive performance. It is also sometimes called generalization error, which is the expected error on new data. Again, so what we do in order to get predictive performance, we divide data into training data set, test data set, and then we fit the model only on training data set. Then we use that then we use the model on test data set to get the prediction for performance. So the goal of machine learning is not to fit existing data very well, but to make the most accurate predictions on new data. So the goal is quite different from trying to estimate the model parameter as accurately as possible. And what I show you in the previous couple of slides is just one-dimensional data, and it's very simple regression. But the data can be anything. They can be multidimensional, they can be continuous, they can be discrete, they can be categorical. So the same paradigm applies. So you divide the data first, fit the model, and then test the model on the test set to get prediction performance. But as I said, the goal is not to fit to the data. So overfitting is actually quite bad for predictive performance. So for example, in this case, on the left here, if your model is too simple, you try to fit the training data, it doesn't fit very well. Also, it doesn't fit the test data set very well either. In this case, the model is said to be too simple. And on the right-hand side, you have a model that is so complicated, it can fit anything. It can fit the training data set almost perfectly. But the problem is that now you overfit the data. You're fitting not only to the pattern in the data, but also to irrelevant pattern, in this case, noises. And then when you use that model on the test data set, you find that it had big testing error. In this case, it said that the model is too complex. It has low training error, but the test error is big. And then you have something in the middle. That might not be just one solution. There could be many solutions, and that would depend on your data. That would depend on how you train the model as well. And also, when I say train the model, I mean fit the model to the data. In machine learning, we use this term interchangeably. So in this case, you might fit some model with intermediate complexity. It fit training data set reasonably well, but not perfect. And then it might have like some good generalization, which means it has low test error. Right, and then to start now, we can start talking about machine learning and touch on some of your questions. So one of the themes that came up a lot is the comparison between machine learning and biology. And I think what we want to convey in this discussion and lecture is that machine learning, although it has some inspiration from biology, is not the goal is not to mimic biology. So they are like modern machine learning and biology are like planes and birds. So machine learning and planes are engineering endeavor. The goal is to perform, not to mimic biology. And this doesn't mean that biology solution is suboptimal. So the scale of that machine learning and plane are expected to perform are quite different from the scale that biological systems operate. For example, the number of neurons in the brain is so much greater than the number of units in neural networks, and the tasks that the brain can perform are quite different from the tasks that we expect machine learning to perform. And I'm gonna hand over the discussion to Tankut.
Okay, thanks, Wave.
Well, hang on. Let me answer the question that come up here. Just so.
Okay.
Yeah. So the question is So the question is the split between train and training data is typically 20/80. And the question is whether there's any theoretical basis of what proportion to use for test and training data. And the answer is you want to use the majority of the data to train the model, and then reserve some to use to test that model, to test the predictive power of that model. But I would say these numbers are more like a rule of thumb rather than anything that has like theoretical ground. That's the way I understand it. So the ratio can be 20/80, it can be 10/90, it can be 15/85. It all depends on the data set and the task at hand. Okay. Yes. So hang on. And another question is about whether data are divided randomly into training set and test set. The answer is yes. So we need to divide them randomly because we want unbiased estimate of the performance of the predictive performance. Another question. Why couldn't you run two separate tests and have one be the training data set and the other be the test data set? Actually, that is possible as well. So it's called cross-validation, and you can. So the idea is that you can separate like the data into training set and test data set, and you can do this multiple times, repeating the process by fitting the model on the train set and then test the model on the test set, and you can then average over like all realization of your splitting of the model into two. Okay.
Should I keep going, or do you want to?
Hang on. Okay. Yeah, I think this question is probably better answered after you heard Tankut and Mingwei. Okay, so I will leave the remaining question for now. Okay. Tankut, you want to take over?
Yeah.
Okay, thanks.
You can see it?
Yep, that's perfect.
Okay. Okay, so what I'll be talking about in my time will be, I'll try to give a primer on deep neural networks, basically. So this is really the reason so many people these days care about deep learning, why AI is becoming like not a bad word again, in industry and in academia. It's because of deep neural networks. And so I'll just try to give you a sense, like an overview of what they are. And in particular, I'll describe the benchmarks, which is what are the tasks that we want them to perform? How do we know that they're doing well? We need to have benchmarks to say that they're good or bad classifiers. And also I'll describe a little bit about what the architectures are, what they look like, how they're constructed, what makes them deep, and how they're trained. So describing specifically what the learning algorithm is. In this case, it'll be stochastic gradient descent. And finally, some interesting examples of how they can fail, like what can go wrong with deep neural networks. Okay, so the first thing to say are the benchmarks. So these are very popular, very commonly used, and that's the main thing. They're commonly used, so you have some kind of point of reference, benchmarks for image classification. That's one Another huge area is natural language processing, and there's separate benchmarks for that. But this, in image classification, it's pretty straightforward what you want to do. You have, for example, with CFAR10, there's 32 by 32 color images. There's 10 categories, and you want your image classifier to, get an image and classify it correctly, right? It sees an airplane and it classifies it as an airplane and not a truck. And this data set, there's the test training split is 50,000 training images and 10,000 test images. Another commonly used data set is the MNIST handwritten digits. And the goal here is the same. See a handwritten digit and classify it correctly, get the right number, right? And this is slightly larger, 20,000 training images. And then there's also a newer and perhaps more challenging benchmark, comes from the ImageNet data set. In this, there's 22,000 categories. Okay, so way more than just the 10 in CFAR10. 22,000 categories, much bigger images as well, 256 by 256. And in this data set, you have 1.2 million training images to train on. And so that's a huge number, and that actually informs the training algorithm that you'll use for this kind of benchmark. Okay, so this is what by benchmark we mean. You build your classifier, you come up with some idea for a neural network, you train it on one of these, and you show on the test set how low you can make the error on the test set. And there's world record holders for different neural networks that do really well on these benchmarks, and they're the ones who get a lot of attention. Okay, so that's just the benchmarks. Benchmarks are important. That's how you push the field forward in some sense. Okay, next is the architecture. So what are deep neural networks, right? So I'm going to describe two major types of layers, two major transformations that are used in deep neural networks. And the first one, and these are also relevant for what's going to come later in Mingwei's discussion of the lottery ticket hypothesis. But the first one is a fully connected layer. So what is it that you want your deep network to do? You want it to receive an input, which is just a vector. Here I labeled it X. So by vector, I mean it has, in this case, 5 components, for instance. And each component, each circle represents some value, some number. And I feed this vector into some function, and it'll spit out another vector. And in this case, the vector I've denoted as y. That's the output. So the input is a vector x, output is a vector y. And we have to specify exactly what this transformation looks like. So for a fully connected layer, the transformation proceeds as follows. You take the input x, multiply it with a vector, here I've denoted w1, and then take that number, send it through a nonlinearity, sigma, and these are popular choices, just some nonlinearity. So the hyperbolic tangent or the rectified linear unit. And then what you get at the end, the output, that's the value of y1. You repeat the procedure with a different vector w2 to get the value y2. And to get y3, you choose yet another vector w3, and repeat the same procedure, multiply, take the dot product of W3 with X, send it through nonlinearity to get the output. So as a final result with this procedure, I mean, you do it all at once. You don't have to do it one at a time. You have a transformation of some input vector X to some output vector Y. And in this case, so I've written here just some vector notation for this transformation, what it would look like. And there's some parameters. Now that's the very important thing about these architectures. There are parameters that you can vary. In this case, the W. The W aren't fixed, and that's in fact what we're going to have to try to change and fit and train to get this map just right. So in this case, for a fully connected layer, you have these three, in this case, this three vectors, and really it forms a matrix. So the parameters for a fully connected layer are just a matrix of values, of numbers, real numbers, right? So that's a fully connected layer. The next would be a convolutional layer. And the principle is very similar. I have, once again, I'm representing these rectangles as taking the various the arrows, summing them together, weighted sum of them, and then spitting out some output. So in this case, but with convolutional layers, they don't see all of the inputs. So in this case, it's just a sum, for instance, of the first three inputs, x1, x2, x3, sum them together, weighted by some vector w, and then output y1, and moving down to get y2, you keep the same w. So that's really the essential difference between convolutional versus fully connected. You use the same w to compute y2, and you're only reading maybe a neighborhood of 3 input values. And similarly, you go down to compute y3 using, again, the same w. So for a convolutional layer, you have a potential advantage, which is that you have fewer parameters to train, right? Before, we had a huge matrix, which had 3 times 5 parameters, so 15 parameters. Here, there's only 3. And one thing that you're able to play with, so you can tune these W's. They can take any real value, but you can also change the size of this convolutional filter, as it's called. So in this case, I took a length 3 vector. I could use length 4, length 5. It depends on the problem, what makes sense. It's a choice, and this is called a hyperparameter. So it's something you don't learn. So your learning algorithm doesn't touch the hyperparameter. You fix it. It's the engineer's supreme insight, fixes the hyperparameter, and then the learning algorithm commences. Okay, so these are just 2, but they're very popular, very widely used kinds of deep learning elements: the convolutional layer and fully connected layer. There's in the ComNets, in the kind of architectures that Mingwei will discuss, I think, in his that was discussed also in the lottery ticket hypothesis paper. There's also a max pooling and an average pooling operation, but and these, what I described is taking a 1D vector and transforming it in these 2 ways. Images, to deal with images, you need to obviously transform a 2D array. And these objects are kind of straightforwardly translated into that setting. It's really the essential ingredients, or the kernel of the idea are you can see in 1D, I think. So that's the reason I presented that. So now, what is it? The question maybe now is what is deep? What is deep learning? What does the deep mean in deep learning? I think it's sort of, that meaning has sort of evolved over the years, but at the very basic level, it just means that there are many layers. And sort of the qualitative picture is that if you have many layers, you're able to process an image at a different hierarchy of scales. But I'm just hand waving there. So deep learning architectures, you can have many layers, and you can mix it up, right? You can, if you have all of these different kinds of layer-wise transformations, you can do convolutional layer, fully connected, convolutional, fully connected, or maybe just do a bunch of convolutional layers and then a fully connected, and then read the output. There's a bunch of, there's some choice. And this is part of the art, the mysterious art of deep learning, is designing your deep neural network. This is what actually the science of machine learning would presumably hope to do. Take this art of designing a deep neural network and turn it into a real like engineering discipline. To have some principles behind why you might use one kind of layer versus another kind of layer. And of course, the architectural choices are informed by the structure of the data, trainability, what's easier and harder to train, and some practical considerations, like how many parameters can you actually store in your machine. So I'll speak very quickly about this one point, which is that why convolutional layers? So one reason you might want to use them is that they can track patterns that have been translated, so moved a little bit. So it's very easy to see in the 1D case, if I have here, the input vector is just 0s and 1, and the parameters in my convolutional layer are such that the output is 0s and 1. 1 is just the filled-in circle. Then if I translate that just one step, the output will also be translated one step, because you're computing each output using the same weight, the matrix that's just translated each step in the convolutional layer. So the reason this is useful for images is that, for instance, if you trained on an image of an owl and it was on the lower left corner of the picture, then you will be able to identify that owl when it is moved to the top right corner, because the output is the same. Using a convolutional layer, the output is the same for both of these translated images. So that's one hint of how the data structure and the problem that you're trying to solve can inform your architectural choices, and why convolutional layers are used heavily in image classification. Okay, and this is just an example from one of the earliest convolutional deep neural networks with it's really just like, I think I've included it here for historical curiosity. So you see what happens here. There's a series of convolutions. You see it, convolutions. There's some additional subsampling layers. These are an extra process that's not, you can't train it. And then at the end, there's some fully connected layers, and then finally the output. So you pare it down to 10 outputs. This was for handwritten digit classification. Okay. So we have our deep neural networks, they have a ton of parameters, and that's really the point. We need them to have parameters. We need them to be parameterized by real numbers. And the idea is to do gradient descent to find what the optimal parameters are. So what is gradient descent? First, like as Wave described, we have some training sets, training data, and from this training data, we want to compute the loss, and that's equivalently the training error or empirical risk. And in this example, I just wrote down the simplest thing you can think of. You take the output of your network, which is y of x, and you compare it to what's the true label of the data, which is y sub a. And you take the mean square. Yeah, this is the mean square error, right? And now think about this function, this error, as a function of w, which is the parameters of your model, right? And you want to change w until you get to the very lowest value of the error. So the idea, the sort of picture is that you're moving on this landscape of the loss. And here it's a very simple landscape. It's just a parabola. And you want to move w so that e gets to its smallest value. The loss gets to its smallest value. And the most straightforward way to do that is use gradient descent. So you change w, the delta w is given by the derivative of the loss with respect to w, right? And here, this is another hyperparameter. This is another thing that you can you fix and then you adjust. You try to find the optimal value of eta. Eta here is just a learning rate. That's what it's called. So it's just a proportionality constant, right? And full gradient descent would require you to take the gradient of E and sum it over the entire training set. But you remember something like ImageNet, there were over 1 million training examples. So computing this sum at each step, at each iteration and updating W is prohibitively costly. So this is where stochastic gradient descent comes in. Okay, I'll wrap up soon, Mingwei, and then you can have your time in the spotlight. So the training sets are too large. This is full gradient descent doesn't really work. Also, the loss function can be complicated. It might have bad local minima. And what appears to solve both of these problems miraculously, it seems, but Mingwei and probably David will have something more to say about this, is instead of using the full gradient, you estimate the gradient on a subset of the training set. So on a mini batch, that's what it's mini batch. So what this is just the procedure for doing mini batch gradient descent or stochastic gradient descent. So instead of taking your entire training set, you take some subset of B training examples. B could be when B equals 1, you just take one training example. That's actually called stochastic gradient descent. When B is something larger than 1, 10, 20, that would be mini batch gradient descent. So you take this subset of the training set and you update your weights on that subset. And now you choose a different subset, and then you repeat step 2, update your weights, choose a different subset. And in this way, you go through your entire training set, but one small batch at a time. And this means that at each step, you're just getting some kind of estimate of the full gradient, but it might be noisy. So it might be a little larger or smaller, or maybe in the opposite direction from the actual gradient. And this kind of noise is what appears to help kick you out of local bad minima. And it's also extremely efficient. So this is the essential ingredients for stochastic gradient descent. That's training. Okay, and I guess the last item is failure. How do deep neural networks fail? And this is, I think, really interesting and also like shocking. So one way that you can trick a deep neural network trained on these enormous data sets is using adversarial examples. So what this is for instance, with the panda image here, you take your panda image and you disturb it by some very, very low amplitude noise. But it's not actually noise. It's a perturbation in a particular direction that is just insidiously chosen so that the final image, which still looks like a panda to us, but the pixels are adjusted in such a way that the classifier, your deep neural network, will take this image and classify it as a gibbon or some other object. And it's so bad you can do this to, well here's where you can, that doesn't seem adversarial, that seems maybe like just annoying, but you can just completely fool these classifiers as well. So starting here with, for example, with the image of a sloth, and you perturb in just such a direction that it misclassifies as a race car. So you even have this kind of control over how it's misclassified. At least in this example, they have this kind of control. So this is an outstanding question, right? What is it that these classifiers are seeing that maybe we're not, that causes them to be confused in this way? Is it a property of the data set, of the actual images, or is it some interplay between the architecture and the images? Are they somehow overfitting? See, these are, and this is an active area of research right now, and it's very fascinating. Yeah, so that, I think that's it. And some things that I didn't include about, so one important aspect is interpretability, right? And this goes to the adversarial examples. Like, why are these DNNs doing what they're doing? This issue of interpretability also goes towards, using machine learning to do science. So in Wave's example, for instance, you had a model for the old example of doing science. You have a model for the pendulum, so you understand what maybe the fit is doing. In machine learning, with these heavily overparameterized models, it's not always so clear what's detected in an image, for instance. So interpretability is an issue. There's also active research in these broader social impact of AI and ML, which include fairness, so eliminating bias from algorithms, and privacy, of course. Somehow learning about a user without actually learning about them. Yeah, and these other points, but I think I'm out of time, so I'll hand it over to Mingwei now.
Thanks, Tankut. Let me share screen. So there are many unexpected phenomena in deep learning. So it's still mysterious to people nowadays, like double descent, random backpropagation, and the lottery ticket hypothesis, and etc. So for my talk today, I will be talking about the lottery ticket hypothesis, which I personally found is one of the most interesting one. Before talking about this hypothesis, I want to talk about a little bit about the idea of pruning. So why are we pruning the model? So as you has already realized from Tankut's talk, the model we are using nowadays are pretty large. So for example, the model we are using, typically the model we are using to classify classify images in ImageNet has more than probably 10 million numbers of parameters. So it's really huge. So actually we want a smaller model to deploy on a device when we use it in daily life, like a mobile phone. And also we want to have a faster inference. So the inference here, I mean, is the prediction. So after the training, you actually want to use the model to do something, right? You want to use it on daily life to help you to predict something and to see what a flower is and whether it is a panda or not. Probably you can do it by eye, but I mean, model can do more. Like neural network can do more than that. So we want a smaller model and we want a faster inference. How to do that? One of the idea is pruning. So when we have a model, we can prune the model by various methods to make it smaller. In that case, to fulfill our goal. So the idea of pruning is that the first step, we train the model to train the whole model, the large model, and then we remove some part of the model by some criteria. So the criteria we are considering today is by the weight magnitude. So remember, there are many weights in a neural net. So after the training, some of them are large, some of them are small. So we assume that the small, like the weight with small magnitude actually do less than the weight with large magnitude. So we can set this as a criteria to set a threshold, and then we can remove some of the weights in the model by with magnitude below this threshold. And then after the removal, we can fine tune the model again. So fine tune, I mean, we retrain the model. So let's say you have a model with 10 million parameters. After the removal, you have only 10,000 left, 10,000 parameters left. And then you will see a little drop of the test accuracy or test accuracy or a little increase of the test loss. So in that case, you will retrain the model from this prune model by the same data set to make it better than before. And this step we call fine tune. And then as you may realize now, you can actually repeat step 2 and 3. So removal and then fine tune. And then after the fine tuning, you can remove the model, remove the extra layers again, and then do the fine tuning. So keep doing step 3 and step 2 and step 3 until the whole process actually fluctuates. So in that case, you can't remove the model, remove any weights anymore. And so this is the main idea of pruning. So I can show you some results of how well the pruning is. So basically on the left side here is just some typical models we are using nowadays. And you can see the compression rate after pruning is it can reduce the amount of parameters by the amount of almost an order of magnitude. And you can see the loss here doesn't change too much from this is for ImageNet. So top one area is from, this is for a CIFAR 10, and the top one area is from, this is for this is MNIST. So the top one area is from more than 1% and still in the 1% area. So we can see the pruning process is very kind of successful in these days. So now we have the questions. So can we train? So remember we have already pruned the neural nets, right? So now the neural net is much smaller than the original neural nets. So actually, can we train the pruned neural nets from scratch? So from scratch, that means that we don't use the full neural nets. We don't train the full neural nets first. We directly train the pruned neural networks, which is the smaller one. Can we do that? And the other question is kind of like similar or corollary from the first one, which is like whether the networks have to be so over-parameterized to learn. So can a small network do the same thing as optimal as the original large over-parameterized model? So the answer to this question is kind of uncertain. So it depends. So there are two ways of training the Pruning model from scratch. So this is the first one. First, we have the large original network. We randomly initialize the full network, and then we train it and do the pruning process, as I have already discussed before. And then we have the prune network, right? So assume we got this architecture of the smaller network, and then we randomly initialize the remaining weights. So we randomly initialize the weights of the prune network, and then repeat 2 and 3. So keep training and keep pruning and keep training, keep pruning. So the result from this process or from this algorithm is that we will find it's harder to train after we prune the network, and it does not reach the same test accuracy as the original large network. So let me describe the second algorithm. So the second algorithm is kind of similar to the first one, but a little bit different. We randomly initialize the full network first. We train and we prune it. But after we prune it, so let me go back to here. Instead of randomly initialize the remaining weights, we reset each remaining weights to its value from step 1. So from this full neural networks. And then we repeat step 2 and step 3. So this is the only difference here. Instead of like randomly initialization, we reset every time after the pruning back to its original weights from the initialization of the full network. What we'll find is that actually it is easier to train and reach the same test accuracy, and sometimes even better than the full neural net. So I will show you some experimental results from Franco and Calvin here. So let's focus only on this model. So this model is already has already been introduced by Tankut in the previous talk. On the left plot here, it represents the time to train. So it's called early stop iterations. So the less iterations you need to use, the less time you need to train the model. So the lower point here means faster to train, and the upper point here means like longer time to train. And as you can see, the dashed line means we randomly initialize the weight. So from algorithm 1. And the solid line here, we reset the weight back to its original full large model. And you can see the training time from algorithm 2 is much smaller than the training time from algorithm 1, and this is the compression rate. So as soon as the model is compressed, the dashed line is already increasing. So that means random initialization doesn't work for compression, because it will increase the training time like once you start compression. But for the solid line here, this it fluctuates around this area until you compress model too large, like to 2.9% of the original model. That means the whole model has the capacity to compress from 100% to all the way to 2.9% of the original model without any longer time to train. And the right plot here means the job, like the test accuracy, and like similar phenomena you can observe. Dashed line represent the model with randomly initialization. So as soon as you start compressing, the test accuracy starts to drop very fast, and you can see to 1.2% of the original net, it's almost below 0.9. So remember that this task is a very simple task. So a simple neural net can already perform almost like 100% of the on the test 100% accuracy on the test data set. And for the solid line here, all the way up to also 2.9%, the test accuracy doesn't drop at all. And you can see here the test accuracy even increased a little bit after you do the compression, like after the compression rate to 60.9% of the original model. So this kind of experiment is like phenomenal. And let's sum up the lottery ticket hypothesis a little bit like in a mathematical way. So fxw is our neural nets. X is the input data and W is the weights. So F is the function of these two quantities and it outputs our predictions, right? And then we have these models which is accuracy A in T iterations. So iteration means like how many times you do the training. So so pruning means we have a mask M. M is a fixed value of binary values, either 0 and 1. And the multiplication sign here is actually element-wise multiplication. So this process, N times W means represent the pruning here. So whenever it's a 0, means we prune that weight. And whenever it's a 1, meaning we keep that weight. So the hypothesis is that there exists N such that there exists a mask such that after the pruning, the number of the weights is much smaller than the original weights. But we can reach a higher test accuracy and with a less training time. So this hypothesis is kind of like very unexpected, because that tells us that, so the hypothesis tells us that the neural net actually contain much smaller, sparse, and trainable subnetworks. And remember from the talk of Tankut talking about the SGD with noise. So even you train the model from the same initialization, but whenever the randomness you set is different, you might result in a different subnetworks. That means the whole full large neural net actually contain multiple, probably like so many of them, like multiple smaller sparse trainable subnets. And all of them, we can call them as a winning tickets or in this hypothesis. That means they can be used to do the classification. And then this subnetwork can be found via pruning, as we have described before. And yeah, so the subnetwork have won the initialization lottery such that you can train in isolation. So once we have this kind of a winning lottery, we can train the lottery directly from the beginning, as long as we set their weights back to their full back to the original initialization in the full network, in the full chain network. Sorry, without training, like in the full large network. So this is the whole idea of lottery ticket hypothesis. So, but nowadays I don't require any too much theory on how to explain this phenomenon. So the previous algorithm I described, actually they originally did the experiment on kind of like a small scale task, such as a CFA10 with 50,000 images, or MNICE with 60,000 images, 60,000 images. So this is the algorithm. But what happens if we try to do the same thing for a large scale task, such as ImageNet with I remember has like 14 million images, and the model size is like 24 or 23 million hyperparameters. So in a large scale task, we only need to include one more step, which we call a warm-up chain. So the same here, we randomly initialize the full network, and then we train the network for several epochs. Epoch means just how many times you run through the training set. So after this warm-up training, we do the same thing as the previous algorithm. We train and we prune, but instead of reset the remaining weights back to the weight from step 1, we reset the weights back to the weight from step 2, and then we just repeat step 3 and step 4. So this is just one difference, and this phenomena can be intuitively understood by a minimal value picture, which will be described by Dr. Schwab in the afternoon. So after his lecture, I think you guys can have a better understanding why this is happening, why we need to warm up, why we need to do a warm-up training for a large scale model and large scale task. Yeah, so basically this is my talk today. Maybe we should, do we still have time to answer the questions?
Yeah, we could try to go through as many as possible.
Okay.
Unless we're booted out.
Yep.
Okay.
So, okay, let me take one. So there's a question about whether taking different training set will increase the efficiency of deep neural network. The answer is usually not if you start from the same data set and you take a different random training set, then the data set should still be the same. It could be different when you take a completely different data set. For example, you could take like it's possible that you might have like a more trainable data set that generalize better, a less biased data set. In that case, it's possible that you can increase the efficiency. But if you start with the same data set and taking a different training set from that data set, then the answer is no. I'm gonna take one.
I think, sorry, there's one question which I think is actually a very good question, and I don't really know the answer to. It's about pooling. Does pooling reduce the amount of computational work, or does it actually help capture features of the image? And I'm not quite sure. Like, it clearly reduces computational work to some extent. Like, it's compressing the image, but does it capture? Yeah, it's. What do you think, Mingwei?
I think like so especially for the max pooling,
yeah,
it helps the model to focus. So if you understand like what a max pooling is, it puts out the, so like in a 2 by 2 matrix. It only put out the number or the value with the largest magnitude, right?
Yeah.
So I think like for the max pooling, it will help the model to focus on the part that is the most important. Like, this is just some intuitive. I would think so. So
yeah.
Yeah. So I think there's like some intuition behind like these techniques, but most of the time the techniques that you hear in deep learning are empirically motivated. It's because it's there because it make the training error lower. It make the model generalize better. It made the training faster. So that's why we need more physicists to be thinking about this problem, so we can understand more why we should do the thing that we do now.
Yeah, there ain't too much theory behind this practical models or practical architecture we are using nowadays.
Yep.
It's really lack of theory right now. Would initializing this to the same weights cause overfitting? So from the basic experiments, it will not for now, because you can see in the experiment that after the pruning and initializing to the same weights, the test accuracy even increased a little bit. So probably because you restrict the model size from the beginning. So certainly there's some kind of method you can use to prevent from overfitting after the renormalization to the same weights. Yeah.
Okay.
How good.
How about the first question by Azim? I think it's a very challenging question, actually.
Yeah.
And my instinct is the question is about that the eye is uses minimal training and doesn't have as many layers as the deep neural network. So that's really, I'm not sure what to say. You might add that, millions of years of evolution helped one arrive at an architecture that's very fast to train. But other than that, yeah, that it's just an interesting problem.
Yeah, it's a lot of parameters that need to be explored.
Yeah.
Yeah, and I think you're absolutely right about like evolution. Like I'm training the eyes to be the architecture it is today. That make it so much better at extracting like relevant feature even before it get to the brain.
Right.
Yeah. And can we train a neural network to write using image refit? Yes, we can definitely train the neural net to write. So there are certain type of networks, we call them generative models. So those type of networks, we use them to learn our data first and then to generate something. It can be used to generate like images, generate texts, generate even, you're talking about writing, like generate sentences and generate words. And yeah, I once read a poet, like poem like written by a machine learning model, and it is quite good.
Yeah.
Now maths are able to predict it.
These are challenging questions.
Yeah.
Is there any method for training that doesn't use gradient descent? Yeah, there are actually many methods in machine learning that doesn't use gradient descent, like clustering and other kind. But I think the question here refers to, because personally I don't really understand or know like how brain trains itself. So
yeah.
So maybe the question here I actually want to ask, like, can a neural net mimic the training of our brain? Something like that.
Yeah.
Yeah, I think that's a tough question.
Yeah, there's a, and
so I don't think this is necessarily related, but there's possibly a niche subfield in ML which looks at not training weights via gradient descent, but selecting architectures via genetic algorithms, or sort of mimicking the evolutionary process of defining some kind of fitness. Probably it would be like, you know, test error or something like that, or training. And defining like a space of architectures. So maybe you can change out the different kinds of layers that you use or the activation functions that you use. And yeah, I think they're able to actually get quite far just with this kind of process.
Mm-hmm.
Ooh, there's so many.
Yes.
Genetic algorithms for image classification. I could maybe, one of the questions that just came in, and I think it's an actually very important point. It's about images of different size and different patients and different shape of tumors and not confuse the computer. I think what I want to say about that is that maybe a huge part of machine learning is getting the data set. And you know, working with deep neural networks is like, it comes after you actually have collected the data, put it in a form that can be understood by a machine, can be read in, and that's a enormous undertaking, and it's not even, yeah, it's especially challenging for like real world applications, right? Because to collect these images in the first place, translate them into something that's used. It's like field work for the data scientist, you know.
Yeah, at first I know, like, one of the most cited papers in machine learning is the publication of ImageNet dataset.
Yeah.
So it's a huge contribution to the community.
Yeah.
And also, like, in industry, they are doing machine learning also for very kind of task. And collecting and cleaning the data actually take like more than half of the time.
Right.
Yeah, so I think there was a question before that I typed in. So the question was, what's the difference between the training process with the data fitting process? So there's no difference between the two processes. So what you want to do is that you want to fit the model to the data, and the process is the same. The difference is the focus. So if you do more estimation and data analysis, then what you want is you want the most accurate like estimation of the parameter of the model. And on the other hand, if you want to do something like machine learning, what you want to do is that you fit a model to the training set. You're still doing the same thing, but now the goal is different. The goal is to get the test error to be as low as possible, but not using the test data set itself.
Yeah. Yeah, and it's extraordinary that the models, like the models we are using nowadays, have much more parameters than the number of data when we do the training, and you can see that it still predicts very well in the test data set. So that's really unexpected, especially in physics and biology. Like imagine you have more than 5 parameters in A to fit the Newton's law with only 2-3 data points. You can't really do that because you will find that there's so many possible ways and neither of them is the correct way, unless you restrict your parameters to the right degree of freedom.
Yep.
Yeah, but in machine learning, it is not the case. That means that we can also generate input for training neural networks and let them evolve. I think that's a, so you guys see Azim's question. I think that's a very interesting idea. I don't know for sure, but like for the for the reinforcement learning in like in AlphaGo or something, they actually play with themselves. So you can imagine that as the case you described here. They generate the move and they learn from their move and then do the next move. And then if it fails, it will do everything again by tuning the weights and finding a better move. So I don't know whether that's one thing similarly described here. Yeah.
Well,
It's time to train.
yeah, so I think there's another question on autoencoders. So right, so I guess before we start answering any question about autoencoder, is a type of a generative model where you feed in the data and the data got mapped into some variable, and then from that variable you decode into what's supposed to be similar to what you feed in. And in this case, after you learn the model, you can just use the decoder to generate new data that is not in the data set. So yeah, I guess the question was, so yeah, so I think it's related to the panda example that you were mentioning, Tankut. And so the question is does it separate or extract the feature of the image into some variable, and then from that variable you add the different noise and it change the original image to something else. Ideally, it should not, but empirically it does. Well, and that's called adversarial attack. So there exists some small perturbation. It can be on the original data set, or say the original image itself, or it could be on this learned variable, and you can just perturb them just very little, and the output can be something completely different from what you would expect. Even though if you are human by eye, you don't detect any change, but the machine doesn't know. So I think this last question is really interesting and important. So what are the best ways to infer principles from a trained deep net? It's really difficult question, and I think it's still like a very much an ongoing research question. How do we make sense of what the model learned?
Yeah.
Is it just a black box that can do good prediction, or is it something that actually encodes some insight that we can learn from? I think there's a lot of work in this area as well. I'm not an expert on it, but maybe you have some comments.
Not really. I you know, like for the example of scientific discovery, you know, you can take one of these deep nets for image classification, train it on X-rays, and notice features that doctors never saw before. And then the question is, what does that mean? Is that something the doctors missed? Is it picking up noise? I think it's a huge question, and something that needs to be resolved in order for deep learning to really inform science moving forward.
Yeah.
Right?
I think that's a really good point, right? Because people say that, oh, machine learning can replace scientists everywhere, but that's not true, right? You might learn something interesting from the data, but at the end of the day, you want to know the mechanism behind those like feature that you learn from the data, and you still need scientists to go and do lab work to actually pin down those mechanisms.
Yeah. Yeah, that's right.
I think we should wrap up and maybe answer the rest of the question, and I think they're going to be posted online.
Okay.
So
Yeah.
Thanks everyone for joining, and I think we are signing off.
Okay.
Thanks, guys.
Thanks.
Yeah, thanks for the questions. Real fun.